Alright, so I think we're recording now. Let's take a look at problem number 4. We're looking at function compositions and also their domain. So, man, I'm all tangled up. Alright. So, f composed with g is f of g of x g is this ratio, this rational function I should say, and f always creates a fraction with 1 in the numerator. The input is the first term in the denominator. That's the input plus 4. So we have a complex fraction, a fraction within a fraction. So let's multiply this fraction by the number 1. But let's write 1 as x minus 4 over x minus 4. So when we multiply fractions, we multiply straight across the numerator, straight across the denominator. We need to distribute this x minus 4 to each of these terms. So in the numerator, when you multiply by 1, you just get that identical thing back. When I take this and multiply it times the first term, the x minus 4 divided by x minus 4 cancel and just give me x. Then when I multiply it times the second term, I have 4 times x minus 4. Alright. Let's distribute the 4 to both of these terms. So some people like to put a coefficient of 1 there just as a visual aid to help them. That 1x plus 4 more x's is 5x minus 16. So there's our expression for this composition. So there's one of my two answers for problem 4a, because it also asks me to find the domain. Alright, so I'm going to get rid of this stuff just to give me more workspace, and I'm going to move my answer up. I don't need that either. Alright, so if I'm trying to find the domain of a composition, I like to recognize that there's two things that have to be true. Our first function, which is actually always listed second, that looks more like a Q, doesn't it? X is the input into G, so X has to be in the domain of G. If it's in the domain, then we're guaranteed to have a y coordinate as an output, but rather than writing y, we use function notation and we call it g of x. That is the input into the next function, f. So this g of x has to be in the domain of f. If it is in the domain of f, then we'll get a y as an output from this function. But we use the composition notation to indicate that we started with x and we applied g, then we took g and applied f. So that's why I refer to it as an assembly line, that it's going straight through here. So let's take a look at the domains of g and f. If we look at, now Every time we find the domain, we always start out saying the domain is the set of all real numbers, excluding any values that cause division by 0, and also excluding any values that would cause us to take the square root of a negative number. We do not have any square roots, but we do have variables in the denominator, so there exists the possibility of division by 0. If we look at the function g, if x were allowed to be 4, 4 minus 4 would result in a 0 in the denominator, and that would be, if you tried to plug in 4 into this function, you would get 4 divided by 0. That is undefined. That would not produce a y value. So for the domain of g, it's all real numbers excluding positive 4. Written in interval notation, we write it like this. Now, this could be our final answer, but we don't know yet, because there might be some additional restrictions that we have to place on x, because the output of g has to be in the domain of f. Alright, so let's look at the domain of f. The domain of f, we can see very clearly that x cannot be negative 4. If you try to input negative 4, you would have 1 divided by 0, which is undefined. So the domain for f is all real numbers excluding negative 4. Written in interval notation, it's written like this. Now, we're not saying that x is going to be in this interval or in this interval. We need g of x to be there. So, we need g of x to be one of two things. We need g of x, the output, this number, to either be in this interval, which is strictly less than negative 4, or we need the output, we need g of x to be in this interval. We need the number g of x to be strictly greater than negative 4. So let's take a look and see if either of the, what's going on when we substitute in for g of x. Alright, so g of x is x over x minus 4, and this is strictly less than negative 4. That is a rational inequality, and I do not believe that you have very much experience with rational inequalities. So let me try to help you figure this out. With a rational inequality, we always want to compare it against 0, just like we do with our quadratic inequalities. I need to add 4 to both sides of this inequality. So let's do that on the next slide over here. X over x minus 4 is strictly less than negative 4 if we add 4 to each side. We'll write 4 as 4 over 1 because I want to add these two fractions together, and to add fractions together you need a common denominator. So I'm going to multiply this by the number 1. Now, when I added 4 to both sides, negative 4 plus 4 is 0. So now I have a common denominator. Now my denominator is x minus 4, and my numerator is x plus, 4 times the quantity, x minus 4. Distribute this through and you'll have 4x minus 16 plus the 4x plus that is 1x is 5x minus 16 and x minus 4. Alright. The denominator, x minus 4, we need to throw out 4 because it would cause division by 0, and this inequality would not be a true statement. We now need to focus our attention on the numerator to get another critical point. 5x minus 16 is equal to 0. 16 divided by 5, which is 3 1/5, 3.2. Alright, now to determine whether to shade or not to shade this, it was clear that I needed to leave 4 hollow because it causes division by 0. Since this is a strict inequality, I need to leave this hollow as well. If it had less than or equal to, I would come in and I would shade that in, but it doesn't have less than or equal to, so I'm not going to shade that in. Now this divides my number line into 3 regions. So I'm going to pick a test point from each region and determine whether this original inequality is a true or false statement. So a number that's less than 3 1/5 that would be a good test point is 0. Between 3 1/5 and 4, not really any great test points, but I suppose 3 1/2 would do. So 7/2 is the same thing as 3 1/2. Well, I guess I could just put 3.5. What does it matter? You probably like 3.5 better anyway. So do I. Alright, 5 would be a good test point in region C. So when x is 0, what do we know about this ratio? Is it going to be less than 0? 5 times 0 minus 16 is negative. And then 0 minus 4 is negative. And a negative divided by negative is positive. There's no way that a positive number is less than 0. So this is a false statement. So since it failed for my test point, it's going to fail for every point in that region. And I'm going to eliminate region A. What if I plug in 3.5? Is my ratio going to be positive? 5 times 3.5 minus 16 over 3.5 minus 4. Now this looks like it's going to be negative. 5 times 3.5, 17.5. Minus 16 is a positive number, but 3.5 minus 4 is negative. So like I said, that was a true statement. So we're going to shade in region B. What about a number like 5? Let's give ourselves a little bit more room. Five times 5 minus 16 is a positive number. 5 minus 4 is a positive number. Positive divided by a positive is not less than 0. That's a false statement. So since it failed for my test point, it's going to fail for any point in that region. And we are going to shade in between here on B. So let's go back and look. If we want the output of G to be less than negative 4, to be in one of our intervals of the domain of F, we need the input over here in X to be between 16, 3 1/5 and 4. We need it to be bigger than 16 over 5 and smaller than 4. Now, what about over here? What about x over x minus 4 being strictly greater than negative 4? Alright, so let's see if we can modify our work over here since it's so related to it. I think it'd be obvious what it is, but we will see. X over x minus 4 being greater than negative 4. Well, I'm still going to add 4, still going to get the same common denominator, add that. So on the left hand side, 5x minus 16 over x minus 4 being this time greater than 0. We get the critical point of 4 because 4 minus 4, and 5 minus 16 equals 0 gives us the other critical point, 16 over 5. Both of these values are hollow because the 4 minus 4 is in the denominator. That's why that's hollow. This one's hollow because it's a strict inequality. It doesn't say greater than or equal to. This divides my number line into 3 regions. I can pick the same test points as last time, 0, 3.5, and 5. And this time when I plug it in, I'm looking to see if I have a positive value. Well, that's going to be true here in A because that ratio was positive here because we said that less than 0 was false because it was positive. Well, now it's true. This guy is false, and this one is true. So well, if we look at the union, not the intersection, but the union, this interval or this interval, then we're saying that over here from negative infinity to 16.5, 16 over 5, and 4 to infinity. These two things together is all real numbers except those two numbers. Okay, we'd already thrown out 4, so that makes sense that 4 was, already thrown out, but now we have to throw out 16 over 5 as well. So that's our domain. For this composition, the domain for fog is all real numbers excluding the 3.2, which I always just write it as an improper fraction, but it doesn't really matter. Exclude that value, also exclude 4. Anything else is fine. Anything else will make it through the assembly line just fine. Alright. Let's take a look at this one. This time the composition is the other direction. We need to find the expression for g of f of x. So again, we're going to get a complex fraction. G always takes the input no matter what it is, and it creates a fraction. In the numerator, it always takes the input. This time the input is this fraction, 1 over x plus 4. The input is the numerator. Now in the denominator, it takes the input, and then it subtracts the number 4. So we would like to simplify this complex fraction. We prefer not to have a fraction within a fraction, so we're going to do a familiar trick of multiplying by 1, but we have to be clever in how we write 1. This x plus 4 is in a denominator. This is x plus 4, so pick a common denominator, and now, with the numerator and denominator being the same expression, this simplifies to 1. So when I multiply by 1, 1 is the multiplicative identity, because when you multiply by 1, you get the identical thing back. Alright, so when we multiply fractions, we just multiply straight across the numerator, straight across the denominator. These two numerators are reciprocals of each other, so they have a product of 1. When I distribute this x plus 4 to both terms, that multiplication distributes over subtraction. When I multiply the first term, again, since those are reciprocals of each other, I'm just going to get 1 minus 4 times this. So let's simplify that denominator. Distribute the 4 and combine like terms. One minus 4x minus 16 and negative 4x minus 15, because positive 1 minus 16 is minus 15 there. Alright. That is my first answer of 2 parts in part B. That's the expression for the composition. Now, let's find the domain for this composition. 2 things always have to be true when you're finding the domain of a composition. X has to be in the domain of the first function. So here, x has to be in the domain of f, and the output of this first function needs to be in the input of the second function. Otherwise, there won't be a y value that comes out of the second function. Alright, so when we look at the domain of f, we can see, let's just write down x not equal to negative 4. We can change it to interval notation in a few minutes. When we write down the domain of g, x is not equal to 4. But this g never sees the x. X always goes into f. What g sees is this f of x. So what we really want is f of x to never equal 4. So f of x is 1 over x plus 4. We temporarily let it equal 4 to solve this equation, so we know if there's an added restriction that we have to place on the domain of this function composition. If I cross multiply 4 times x plus 4 is equal to 1 times 1. So let's distribute and solve for x. 4x plus 16 is equal to 1. X is negative 15 over 4. We don't want that. We want to make sure, because if you were to plug in negative 15 over 4 into f, f would have no problem calculating that the output is 4. But then when you go to plug 4 into g, you're going to get 4 divided by 0, which is not a y value. So this negative 15 over 4 would not have a corresponding y value. Therefore, we have to throw out this negative 15 over 4 from the domain. So on our number line, we're throwing out negative 4, and we're also throwing out negative 15 divided by 4, and that's greater than negative 3 3/4 is greater than negative 4. So we're throwing this out. So here is the set of numbers we need to describe in interval notation to give the domain of this function composition. So the domain of golf is the set of all real numbers excluding negative 4 and also excluding negative 3 3/4. So here is our second answer for problem 4, part B. Now in C, it's super easy. We're just going to plug in 2. We don't have to calculate any kind of expression. We don't have to find any domain. We've already found the domain for G composed with F. G composed with F is here, and 2 is not one of the numbers we threw out. 2 is in my domain, so I should be fine getting a Y value. Alright, so let's let x equal 2 for this function f. We have 1 over 2 plus 4. That is 1/6. So we take 1/6 and we substitute in. We often say we plug it in to the function g. So in the numerator, instead of writing x, we write 1/6. And in the denominator, instead of x minus 4, it's 1/6 minus 4. Alright, rather than using a calculator, I am going to do what? Multiply by 6 over 6, and that will get me a 1 in the numerator. The 1/6 times 6 gets me a 1 here, minus 24. So I believe that we have negative 1 over 23 as our answer. So if you evaluate this composition, G composed with F at x equals 2, you'll have a y coordinate of negative 1 over 23. Alright, I hope that helps. I'll do the next problem in another video.